organize our data in histograms. So we divide the spectrum by classes with a lower and an upper bound, and then we get how many counts we have of droplets that fall within that class of velocity or in that size class. This is usually how we do it. But it comes the second question, right? So we have all this data. How can we do it best? Well, the answer from my point of view is that we do it best because we want to understand the reasoning behind organizing our data. So we are not organizing our data in histograms just to present data, right? But because we have a physical process, an atomization mechanism, a transport mechanism. We want to know something about the atomizer or the spray because we have a research question. We are just not presenting data. We have a reasoning behind the way we organize our data. So basically what, concretely in practice, what does this mean? We have all this data. We sort, for example, in terms of drop size, we sort this data by size classes. And then for each size class, we compare to the total number of droplets, and then we get these histograms, which we call usually drop size distribution, okay? This is how we usually organize our data, but how can we do it best? So we have these questions. What does it mean? It means organizing our data. How can we do it best? By understanding the reasoning why we organize it. But there is one, from my point of view, very, very, and probably the most important question, which is why should we do it? And let me give you two examples of why should we be concerned about the way we organize our data in spray characterization. The first example comes from a paper I found some years ago in a conference. So you look at the results of experiments, and we are looking at a volume-based probability density function, which means it has no units. So if you sum all the probabilities, the result must be 1. And the squares are the experiments, and the bars, the simulations. And the authors said that the simulation is able to describe what you found, the experiments. But have you noticed that the classes in the experiments are irregular and that the classes in the simulations are regular? Which means that the width of the bins in the experiments is different from the smaller sizes to the larger, while the bin width is the same, it's regular for the simulations. And this is something which is different, and I will show you later what I'm meaning, what is the, let's say, the observation, the critical thinking I'm referring to. And the second example is a little bit more serious. It is a paper in a very well-known journal, Physics of Fluids, which has to do with COVID-19. So this is a very serious matter, as we spoke earlier at the beginning. And in this case, the authors wanted to characterize the drop diameters of saliva, which comes from coughing, sneezing, or eventually talking. And they wanted to use a function in their analysis. So they have this data from other authors, but have you noticed that you don't have any values for the frequency? And I was a little bit puzzled. What are the values of the frequency? Okay. And then, but fortunately, they present the fitting, which is a Rosen-Rambler, and they even give us the parameters of this past fitting. So I was very happy, and I wanted to know the values of the frequency. So I plotted exactly the function that they were sharing. And I just made the adjustments to the maximum. And it's not the same. So I was just wondering, well, there is something wrong. So this this justifies my argument. We should be very, very careful in the way we characterize sprays, because honestly, our work is very, very important. Okay, so how can we do it best? Well, the first question would be how many classes, right? let's give you just an example of this. One of the most known rules is the Sturgis Rule. So this defines the number of classes. But several authors say that this rule does not work when we have samples over 100. Let's say we have more than 100 measurement of droplet sizes. This doesn't work. And how do you justify this? Easily, you just increase by 1 order of magnitude, and now you can see the detail in my distribution, which is bimodal. So it has 2 peaks, right? Probably from 2 atomization mechanisms or an influence of the transport. I don't remember. But the idea is that the Sturgis rule is not adequate, and this means that we must have a criterion to choose how many classes. And basically, when you build a drop size distribution, how should you choose? They shouldn't be too big that you lose detail, like the Sturgis rule example I showed, but they shouldn't be too small that you get too many empty classes and, as I will show later, some noise. So basically, you have these 2 approaches. Either you use regular bin sizes, and there are other rules available in the literature to help us decide. The 2 first, the Scotts and Friedman diaconese, they give us a suggestion for the bin size, so the size between the lower and upper bounds of each class, and the Rice rule gives us the number of classes. But you can also have, as you saw, irregular bin sizes. When do you have the situation? Well, probably if you use, for example, a laser diffraction technique, mostly known as a Malvern, to measure your distributions. The data that this technique provides is usually based on irregular bin sizes. But how do you decide this irregularity in the sizes? Honestly, for me, we need more research. There is no criterion up to now which is easy to apply to our data. So I think this is a field open for further research. The second question would be, okay, but what kind of distribution am I going to represent when I'm analyzing my data? And here we have 3 usually different options. The first one is that you take the counts of droplets in each bin and you divide by the total number of droplets. So this will give you a number-weighted drop size distribution. But if you weight by the area or by the volume, you get area-weighted or surface-weighted drop size distribution and volume-weighted drop size distribution. So how should you choose? Well, for me, it depends on the physics, on the research question. And let me move a little bit forward to explain this. Because once we plot and have our histograms, we have a lot of data points in our mesh, for example, or different conditions, different fluids. So we have a lot of data, so which means a lot of drop size distributions. And it's difficult to present all these distributions in our papers, in our knowledge. So we basically use mean diameters. So the mean diameter of a number weighted is the arithmetic, then you have the most known SOTA mean diameter, and then you have the mean diameter of a volume weighted drop size distribution, the Brucker. However, the most known is the SOTA mean diameter. However, we could also express this in other terms. Instead of using arithmetic, SOTA, and the Brucker or Herndon, we could use number weighted, area weighted, and volume weighted. Why this transition might be important? Because it will focus you on the physics. What do I mean by this? For example, why is the SOTA mean diameter or the area weighted mean diameter so important in combustion? Because combustion is a process that leads to the vaporization of the droplet. And the vaporization is a physical phenomenon occurring at the area of the droplet, right? So obviously, from the physics point of view, it's the most appropriate mean diameter. And in fact, it's the one which produces the best correlations because it's grounded on the physical phenomena of heat transfer occurring at the surface of the droplet. Another example, think about the atomization efficiency. which is a preprint that I've made and I've included in the file that I've shared. I honestly wasn't expecting to find, but I did, that actually the sort of mean diameter or the area weighted mean diameter is the correct diameter to characterize the atomization efficiency. It is something that I eventually deduced. It's not a choice. It's grounded on a physics, and it's logical. Why? Because the efficiency of atomization, when you atomize, you are changing the surface energy at the interface of a ligament, for example, into multiple droplets. And the efficiency is calculated or obtained by the difference or the amount of surface energy you need in this process compared to the total amount of energy that you put to produce your spray. So there is a physical reasoning behind using this mean diameter. And so when you express in your language this number weighted, area weighted, you are grounding your explanation honestly on the physics. That's what I think. And the third and final question that's going to answer a little bit what I've talked about in the beginning is what should be the bin width. Now, in terms of language, we are not speaking of probability of occurrence, but of probability of presence, which is closer to quantum mechanics, right? And if you change the bin width, it means that you have more classes. So obviously the frequency will lower. So I don't know if you understand what I mean relatively to the first example. In the regular classes, you just need to change the number of classes and you change the position of your distribution. So from my point of view, this is what these authors did, which I don't believe it's the right approach, okay? So what is the right approach? It's not to present the frequency distribution, but the probability density, where you divide each frequency by the width of your size class. And now you can compare different distributions with different number of classes. And this is, from my point of view, what the other authors should have done. And this is the best way you can represent. Obviously, when you decrease too much the bin width, as you can see, you get too much noise. And this is going to be important later in my presentation. So basically, this is how, from my point of view, how can you do it best? It's by answering these three questions and always grounding the way you characterize your spray on the physics, on the research question, on the thing, the process you want to investigate. But let me ask you another question. What matters most in spray characterization? Because in my research work, people always told me, you have to measure a lot of data. And I started to wonder, but do I need more data or do I need more information? And I will show you that data and information are two very different things. So for this, I have to start with a little bit of my story. When I was a PhD student, I was presenting a paper at the Lisbon Symposium that Professor Azade already referenced. And this is a very well-known symposium on the application of laser and right now also imaging techniques to fluid mechanics. At the time, I was a PhD student. Right now, I'm part of the organizing committee, so it's a privilege. And at this conference, I presented a paper. And as you can imagine, we always try to be clear about the uncertainty of the data that we are presenting. And at the end, there was this researcher, now a colleague, Professor Yanis Adaloupas from Imperial College, who did a very simple comment. He said, oh, we are still using Tate. What was he referring to? Well, if you want to express the uncertainty of your drop size measurements, usually we used the paper of Roger Tate from the I class of 1982. where he studied the accuracy in the way we represent drop size distribution. So what it's in this paper, basically, he quantified a percent deviation between the actual cumulative distribution and the one based on the number of samples that you measure with your technique. So what I did at the time was simply to just take this correlation, see the number of samples I had, and people always told me you have to have a lot of samples, more than 10,000. I usually had 50,000, but I was doing experiments on spray impingement, so the data rates were very, very low. So I took a lot of time to make a single measurement, but I eventually got to 50,000, and I got a lower percentage deviation. But he told me we are still using this state, and I asked myself, why? Yeah, why are we still doing this? And at the time, I remember I was reading these papers that use the maximum entropy formalism to extract a function, a mathematical function that best fit our discrete distributions of drop sizes. And I was really interested in that. And so I came across this work by the known Claude Shannon. So he's the father of the information age because of this paper he wrote in 1948 on a mathematical theory of communication. So Shannon wanted to quantify information. So not in terms of semantics or the context, but on terms of quantity, okay? And in this case, this is a wide and a very broad field of research, information theory. And this basically means that he quantified by the Shannon entropy. He used the word entropy because, as you can see, the formulation, it's very, very similar to the one developed by Boltzmann for the thermodynamic entropy. And this is a measure of the information. So it means that when the information entropy is maximum, from the point of view of spray characterization, it means that every measurement counts. So every measurement will give you more information. And sometimes when it's a null, so zero, or very, very low, it means that, well, you already know what you have. You don't need more information, or you don't need more measurements. So, and also, as you can see, it is a parameter that depends on the distribution probabilities. So it doesn't depend on the size corresponding to each probability. So I just thought, well, could I use this? So the first thing I from the experimentalist point of view is my sample size large enough? So that was my problem. And I have a very low data rate. So is my sample size large enough? And the answer usually is yes, if the statistical uncertainty is sufficiently low. So what is a statistical uncertainty? Well, a statistical uncertainty must have three characteristics. The first one is that it should be maximum for a uniform distribution, which means all classes or the size representative of each class must have the same probability of being present in the spray. Also, a small variation on the class probability leads to a small variation on the uncertainty. And finally, it depends on the distribution itself. So what is the parameter that we usually use? It's the uncertainty based on a confidence interval, thus the z coefficient, on the standard deviation of our measurements, on the sample size, or the square root of the sample size, and if you want it in percentage, you divide it by the first moment of the distribution. So the standard deviation is the second moment, the mean of your distribution is the first moment. So it is a concept that fulfills all the three conditions, but it's based on the distribution moments. And people feel comfortable with this parameter because it's actually based on information of your droplets, and it is correct to quantify the statistical uncertainty using this parameter. But I will show you some of the limitations of this. What about the information Shannon entropy? So the information entropy. Well, the Shannon entropy also has all those characteristics. It is maximum for the uniform distribution, and this is, and you can deduct this. Also, if you generate little small changes in the probability, obviously it will generate a small variation. And obviously it depends on the distribution because it depends on the probabilities. But because we may have different distributions and different maximum values, I thought that probably the most reasonable way was to use the normalized Shannon entropy by the maximum value. In this case, every time I compare it or use it, I'm always expecting values between 0 and 1. So what happens when I apply this while I'm measuring, while I'm acquiring more data? And this is what I got. It stabilizes. And this is precisely the insight that allowed me to understand the difference between more data and more information. When it stabilizes, it means that I'm acquiring more data, but I'm not acquiring more information. I already have the distribution, okay? And you may think, okay, but there are some situations where you actually need more data, and I will give you examples of that. But the thing is, it stabilizes. So what I did was, considering several types of mathematical functions used to characterize drop size distributions, for example, the log normal, variable, gamma, and so on, and Ukiyama, Tanasawa, Rosen-Ramler, I just simulated for several possible distributions, and I understood that they are very, very nicely correlated with the normalized Shannon entropy. So this allows me to have a parameter that quantifies exactly the same as Roger Tate, which is the deviation between the distribution that I know and the distribution I get with a certain amount, a certain sample size. And this will give me a statistical uncertainty based on the information theory. But if it stabilizes, it means that I need a criterion. And honestly, I wasn't very comfortable using the normalized Shannon entropy because of the meaning. I couldn't understand the meaning. I can understand it, the meaning in terms of the distribution moment, so the parameter I used before, or people usually use. But in terms of the normalized Shannon entropy, I was a little bit, I wasn't convinced. So I look at some papers, and one of the things I noticed is that in my measurements, I have a variation. So there is an entropy rate every time I add one more data point. And what I found in the literature is that eventually this will lead to a limit. And the area, which means if I sum all the variations of the entropy rate as I increase the number of samples, the area in this plot is what researchers call the excess entropy. So for example, if I'm able to reach my final distribution very quickly, I produce very small amount of entropy. And from the thermodynamics point of view, this is interesting, right? So, and if it's large, it means I have to acquire more data just to get the right and the stabilized distribution. And so the meaning, it's very, very simple to understand. It is the amount of memory gain or the cost of amnesia if all data would be suddenly lost, which is something that the experimentalist doesn't want, right? But this has meaning. And in the case of the phase Doppler technique, this limit is very easy because this limit, if it stabilizes, it's 0, right? So taking this excess entropy, I began to develop a criterion of convergence because that is something that is very well used in to use the statistical uncertainty to define how many droplets you should have in your spray, when you should stop measuring. So basically, convergence is when the slope between the median excess entropy and the excess entropy of the total number of samples, it goes to 0. Let me give you an experiment of the application of this criterion compared to the other one. Let's say a text case. We have 10,000 samples, log normally distributed, but let's simulate that from a certain point in time while I'm measuring, the spray changes. It begins to malfunction, and it produces a different distribution. So after 10,000 samples, the distribution I would get would be a very different one from the previous one, right? So are the usual and the typical criterions enable me to find this, to find that there is a problem in spray? If we use the criterion based on the distribution moments, if the distribution alters and I made the stopping criteria at 1%, it will lead to the need of a lower number of samples. So because I'm adding more data. And this parameter is not sensible to the change in the distribution because my spray is different, right? And what happens to the excess entropy? From the point of view I begin to change the distribution, it begins to change. It doesn't stabilize. So it will tell me, no, please acquire more information because you don't have enough information. So if we use the excess entropy, we would get the second distribution changed by the change of condition. While if you use the typical parameter based on the distribution moments, you would get this distribution because it fulfills the stopping criterion. So I hope to convince you that this is a very limited way to perform your experiments. So the excess entropy is more relevant to our measurements because it is sensible to changes in the distribution. And what are the implications of this? Well, let me give you an experience. I was measuring drop impact, so spray impingement, and I was measuring it very close to the wall. It's very difficult to measure because you have droplets coming down, droplets going up, secondary droplets, and it means that you have a very low data rate in your measurement. So it's very difficult to measure. And if I had used the information theory approach, what would happen to my measurements, to the quality of my measurements? So on the bottom part, you see the number of samples, and you see the dash bars, which has the full data that I measure at the time. And when I developed this approach, what if I use the information theory approach? And you see the gray bars are low, which means all data I acquire more than those bars, it means that they are not providing more information. And as you can see, for the number-weighted arithmetic mean diameter and the volume-weighted mean diameter, the differences are not relevant. So I could have used much less data because I have enough information. What about the velocity? Exactly the same. Both mean velocity and the fluctuation for a certain size class. And why is this important? Because I forgot to tell you that this spray is intermittent, which means that my data, why I needed to acquire more data? Because I was going to divide it in time beans, and each time bean has a much lower quantity of data, right? So if I had used the information theory approach, what I found out, obviously much later, is that I could have saved almost half of the time. So I could measure, for example, if I had used the information theory approach, double my conditions or double the experiments. So what I found is that the information theory approach from the experimentalist point of view will help you to have quality in your measurements because you are able to evaluate if you have or not enough information. Now, I've covered what does it mean, how can we do it best, and the importance of information from the experimentalist point of view. But can we use it, the information theory, to acquire knowledge? And what I'm going to share you is some of the work that I've published last year and developed last year. That has to do, well, not last year, I started this in 2016, so 4 years ago, which has to do with what I call drop size diversity. Now, drop size diversity is a term that I've introduced last year, so something that I published and proposed in the literature last year. So nobody uses this. This is what I'm saying. But I hope people understand it and begin to use it. Because, for example, in many applications, let's say, for example, in the pharmaceutical industry, they want to produce a powder. So they mix the polymer with a solvent, and they use an ultrasonic spray, and then there is a spray dryer to dry the solvent and produce particles of powder from which the pharmaceutical industry produces their pills, right? So it's very important for them to have droplets of the same size. So they want to quantify what is called the spray uniformity degree. By uniformity, we mean having droplets of the same size. What is the opposite situation? Is when you have drop of multiple sizes and all the sizes have the same probability of being present in the spray. So I would say the sizes have the same relevancy in your spray. So can I use the normalized Shannon entropy to quantify the spray uniformity degree? Well, but first I have to ask, how do you characterize it? Usually we use the relative span. And for those who work in sprays, they probably have used this parameter, which is a good, but I will show you, very, very limited parameter. How do you use it? Well, you calculate it by considering the cumulative distribution function. And you take the size that represents 10% of the droplets and the size that represents 90%, and this will give you an interval, and you divide by this range, let's say, by the size which represents 50% of the droplets. So having more droplets of the same size means that you lower your range between the size that represents 10% and 90%. Or, and this is what I found very strange, if the distribution is shifted to larger sizes, the size that represents 50% will lower the relative span, but honestly, I have to ask, why is this a less, let's say, a spray with a lower uniformity degree? Why? I don't understand it. So to understand it, I tried to use, well, maybe I could use the normalized Shannon entropy. And so in 2016, which is a paper I already also put in all those papers I share with you, I used the normalized Shannon entropy to propose a new way to quantify the spray uniformity degree. But I received a very interesting critiques by colleagues from the University of Saragossa. And they told in their paper that this parameter had limitations. And the best parameter to quantify the spray uniformity degree would be the volume-weighted standard deviation. And I got curious, right? Because someone criticizes your work, you get curious. So, okay. So what is the point? Let me share you the challenge that my colleague made me. And I will reproduce it with a simple experiment. Take, for example, this spray. It has a certain value for the normalized Shannon entropy, and it has a certain value for the volume-weighted standard deviation. And I just thought, well, what if I flip the probabilities, right? I use the same size classes and I flip the probabilities. Well, this is a different distribution, but it produces the same values for these parameters. Okay. And now the experiment that my colleague shared to me, but he said to me, Antonio Lozano, he said, but Miguel, you take these probabilities and you randomly distribute it by the size classes. You will get the same normalized Shannon entropy, but a very different volume-weighted standard deviation. And honestly, I look at this distribution and I felt that it was had a much lower uniformity degree. And I just wondered, why? Why is this happening? And this was a very interesting journey that let me just share with you with two very simple experiments. Let's say we have only two drop sizes, 10 microns, 50 microns. So if you have all droplets with 50 microns, all these parameters used to quantify the spray uniformity will give you the value 0. Now let's add droplets of 10 microns until you have a situation where you have all droplets of 10 microns. What will happen? I look at one parameter, normalized Shannon entropy. I look at the volume-weighted standard deviation, and they have the same behavior. I look at the relative span. Well, it increases, but the behavior a little bit strange, right? And what I would expect is that the normalized Shannon entropy is maximum when all kinds of droplets present in my spray have the same probability of being present. And the standard deviation also expresses that. So let's continue to add more 10 micron droplets and reduce the number of 50. And you see exactly the same behavior in the normalized Shannon entropy and the volume-weighted standard deviation. What about the relative span? Very strange, right? Why is the maximum close to 70%? Very, very strange. But at this point, I thought, well, sprays are made of multiple sizes. So I should have at least not 2, but 3 sizes. And so in these plots, W1 corresponds to let's say, the amount of droplets of 10 microns in the total sample. W2, it's the amount of droplets of 20 microns, which is double 10, and that's double again, and 40 microns, it's W3, which is not represented, but it's the remaining part, right? And so what happens when we begin to add droplets of 20, then 10, and so on? What I would expect is that the normalized Shannon entropy is maximum when all droplets have the same probability of being present in the spray, which is about 1/3 in W1 and 1/3 in W2. And when I look at the map, it corresponds. How about the volume-weighted standard deviation? This is a little bit strange. It is maximum when I have, almost half of 10 micron droplets, almost no 20 micron droplets, and probably half of 40 micron droplets. And I noticed that the relative span has a pattern very similar to the volume-weighted, and I understand that because it depends on the sizes of droplets, while the normalized Shannon entropy only depends on the probabilities, right? However, I don't understand why the relative span has a maximum around 70%. And so when we look at the distributions where you obtain the maximums, this is what I had the insight. Because I finally understood that the parameters are not competing. Because this is what the paper of my colleague expressed, is that he was using both parameters in competition, but they are not competing. They are simply answering different questions. So what is the question the maximum normalized Shannon entropy is answering? How many different drop sizes are relevant in my spray? And what is the question for the volume-weighted standard deviation? How different are relevant drop sizes in my spray? These are two different questions. I'm saying this because when we speak about the spray uniformity degree and you look that in textbooks, usually we use the expressions, it is a polydispersed spray. Or you use the expressions, the size dispersion in the spray. But honestly, when I look at these results, I see that these expressions have different meanings. What about the relative span? Well, honestly, I don't know what this is. So from my point of view, the relative span is not a good parameter to quantify what now I will call the drop size diversity. But let me just give you another thing. When you look at the maximum volume-weighted standard deviation, you see mainly 2 sizes, 10 microns and 40 microns. And you see how different they are, right? But why, if I didn't distinguish these questions, if these parameters were competing, why, when I have only also 2 sizes, but they are much closer. Why is this a less polydispersed spray? So this justifies the difference in the meaning of these words. So in drop size diversity, the normalized Shannon entropy has to do with the polydispersed sizes. Poly means many. So it's a parameter that quantifies how many different sizes are relevant in my spray. And the volume-weighted standard deviation quantifies a different thing, quantifies the size dispersion, which is how far apart, how different are the relevant sizes in the spray. So the first quantifies the polydispersion degree of drop size diversity, while the later quantifies the heterogeneity degree in drop size diversity. And this was something I've introduced last year, which I think gives a little bit more clarity into this uniformity degree of the spray, which is very important in many applications. Now, what about the future, right? And I'm ending my webinar. About the future, I would like honestly to share just 3 curiosities of several that I found in spray statistical characterization. These curiosities are the physical meaning of probability functions, complexity, and redundancy, which is the last one, very funny one. So the first one is for the future of spray statistical characterization. Often we adjust a mathematical function, log normal, Weibull, Nokia-Matanasawa, gamma, Rosen-Ramler. We adjust a function, a mathematical function, to our measurements. Why do we do this? Because from the simulation point of view, that's very important. When we use only the moments of the distribution, we are losing information. If we are able to capture the entire distribution through a mathematical function and transport that function, then I'm transporting and I'm not losing information. So I'm using the entire spray, right? But the question is, why a log normal? What is the physical meaning of a log normal being the best fitting and not the gamma distribution or a Rosen-Ramler? So, and just to give you an example, for example, there is the very well-known Galton bar, that it's a very simple experiment that explains why we have normal distributions. It's because each sphere has a probability of 1/2 to go to the left or to the right. And in the next row, it's exactly the same. So the normal distribution is the result of an additive effect of choices. And there is a paper that mentioned this and tried to explain the meaning, the physical meaning behind a log normal distribution. In this case, the distance to the left or to the right is exactly the same. What if the effect is not additive but multiplicative? Which means that if the sphere goes to the left, it will move in a distance which is divided by a certain constant. And if it goes to the right, it moves toward a distance that is multiplied by a constant. And the result of this very, very simple experiment is exactly a log normal distribution. So the log normal distribution is associated with multiplicative effects. What is the physical meaning of that for a spray? I don't know. The next example is the work of Emmanuel Villermo on his paper on fragmentation, an excellent paper, because droplets we know that come from ligaments. And he describes ligaments like this assemble of blobs with different diameters. And once the ligament breaks into droplets, the distribution of these blobs at that time should follow a gamma distribution, and this is the distribution that will best fit the spray characteristics in that point in time. So the use of a gamma distribution is a process that is temporal, I would say. What is the physical meaning of adjusting a gamma distribution to a spray? So this is a question I have, let's say, spoke a little bit about in my last paper that I also share with you on spray characterization, but I think this is a very interesting question for future research. The second one is complexity. Now, in information theory, if you look at the information parameter, the Shannon entropy, it will move from, let's say, a perfect order, a crystal, where if you add one measurement, you don't need to measure because you already know what you have. So any measurement does not add more information, does not add no information. However, if you have a chaotic system, then you have maximum information. What does that mean? It means that you need to acquire data because the system is chaotic. So every data point is important to understand what is happening, right? But in complexity, you have this disequilibrium, which is the distance between any distribution and its chaotic expression, okay? So complexity comes from the product of these two quantities, information and the disequilibrium. And complexity expresses pattern. And for me, that is important because atomization mechanisms should produce a pattern. So I wonder, can we use this to try and develop a little bit better how we characterize sprays? So I had some years ago a master student that studied, because there are different ways to express the disequilibrium, thus different ways to express the complexity, to vary the number of classes and see the effect on this parameter. And we found some differences and eventually some maximums. And we began to explore this, but honestly, I have also other research works to do. So this is something that is still open in my horizon. So can we use also this parameter to improve the way we characterize sprays? And the final curiosity is redundancy. I mean, I was just wondering, in our instruments, sometimes we spend so much money, right, to have a precise instrument because we want precision in the way we measure drop sizes. And so I just started to make some, very simple experiments with truncated data, right? So see how far can I go and how truncating data would influence my measurements of the spray droplets. So what do I mean by this? This is a distribution. Where does this distribution come from? It comes from data, right? And for example, in the phase Doppler, I had one data set that was able to give me up to the 4th decimal part. So which means that each data point is made of 2 parts, right? An integer and a decimal part. Now the decimal part, I know that varies between 0 and 0.99999, right? So I was wondering, okay, so what if my measurement system is cheap and I'm able to measure accurately at least the integer part? For example, in this distribution, what would be the distribution if I just consider the truncated part of the integer? And this is the result. And I was wondering, well, why do I have, for example, so many droplets with 50 microns and so low number of droplets with 51? So when I look at this, I see, well, probably this is something that has to do with the resolution of my instrument. And then I just, okay, what is the distribution of the decimal part? Well, if it's between 0 and 0.999, obviously it must be a uniform distribution. And when I look at this, I say, well, but this is chaotic from the information theory point of view. So why is my measurement 47.6419 and not, for example, 47.7183, right? So what I start to wonder if it's this decimal part redundant. So this is a very curiosity, right? So what if we plot the decimal part and the integer part for the measurements given by my instrument? Do you want to see? Oh, this is resolution of the instrument. Why is the instrument giving me this data? so regular in terms of the decimal part relatively to the integer part. This is not what I would expect from a chaotic process like the atomization of a liquid is. So I just wonder, if the decimal part is redundant, I could replace it with, let's say, a random number. And what is interesting is that in the previous result, there is a function in the language MATLAB that allows me to see how many unique values I have in, let's say, a data of 50,000 samples. What you are seeing is the data of 50,000 samples. But in 50,000 samples, I only have 498 unique values. And this is a problem of resolution. But if I consider the decimal part redundant and replace it by a random value, I would get 50,000 unique values, obviously, right? And I just thought, well, what is the difference produced by using this, let's say, play, right? And the line is the mean diameter obtained from the data I retrieve from my instrument. And the points are several simulations where I randomly produce a decimal part and add it to the integer part. See that the bias is of the nanometer order and that the standard deviation is also of the nanometer order. So which means that if I consider the decimal part redundant and add it for whatever purpose, a random number, I still get the same mean diameter. So what is the meaning of this? I still don't know. So at the end, honestly, what is the final message of all this? Stay curious. I think that's the best thing we need to do, not just to focus on data and presenting data and just pouring papers. It's to strive and to stay curious about these things, because some are probably very simple, probably don't have any meaning, but if we don't strive to stimulate curiosity, we sometimes stagnate in fields of research like I felt was the spray characterization field. While if you stay curious and you keep moving forward, even if it seems, silly, just keep doing, because stay curious is the best message I can give you. So finally, if any one of you, besides obviously Professor Maziar, who I already wants to collaborate with me in this field, please feel free to send me an email and I'd be happy to collaborate with you in this field. So thank you for your attention. I'm open for any questions you may have.
Nice presentation. Thank you, Dr. Panao. Now we can listen to the questions or comments of professors and then students. You can ask with voice or you can type now. I will allow you to type in the chat box. We are ready to hear you.
Thank you, Professor. I have a question about disequilibrium in the complexity. I don't understand what the means of this disequilibrium that you explain in the complexity, and I don't know how you measure and write a diagram and measure this complexity in your data.
Yes, it's very simple. The Shannon entropy depends on the probabilities. The disequilibrium has different ways of being expressed, but is also expressed in terms of the probabilities, okay? There are different expressions for this disequilibrium. So once you quantify the disequilibrium, whatever is the method you use, based on the probabilities that you have in your data, then you just multiply the two and you have a measure of complexity. The open question is, what is the meaning of this for your spray, okay? Or how can you use this parameter to improve the way you characterize? Now, the attempt I did in that case, for example, was that I wasn't, honestly, at the time, I wasn't aware of the rules that were in the literature to define the number of classes I should use, okay? And what I started, and still haven't finished, is to wonder if I could use, for example, the complexity as a parameter to help me decide the number of classes that I should use to represent my data. So, but that's unfinished. It's still open for research. But and also, if you allow me, I haven't studied complexity enough to understand what other meanings this parameter or this idea, this concept could mean from the point of view of spray characterization. So it began as a curiosity. There is some research I did with a master student, but it's still under development.
Is your meaning that maybe a spray one injector has a more complexity than the other injector, and maybe we can find this parameter in our data?
Yes, for example, if you are able to establish a link between the complexity as a parameter and the kinds of physical insight this parameter can give, then eventually using that link, you could compare different atomizers, compare what is the reasoning behind it. From my point of view, up to the knowledge I have on the topic, which is not very much, is that complexity is associated with pattern. And patterns in our sprays we obtain through the atomization mechanisms, which not only have an expression in terms of the energy used to change the surface energy to produce the droplets, but also on the temporal events that lead to those changes to that atomization process, and also in terms of the transport of the spray. Because when the droplets are interacting with the surrounding environment, they will be transported and organized also in different ways, right? According to that interaction. For example, larger droplets will be less affected by the surrounding air, while smaller droplets will be more affected by the surrounding air. So this will redistribute droplets up to a certain level, right? So this will generate somehow a pattern. Could complexity be used to provide some physical insight into these kind of patterns? I don't know.
And just a suggestion, when I saw the picture about the meaning of your formula, really I remembered about variational calculus and the problem that particle may pass a short distance between two points, and I think that maybe this formula depends on something like this minimum surface energy and something like this, I think.
Eventually. As I said, this is still an open field. So if I understood correctly, the question, you're still referring to the complexity?
No, about the first problem.
Oh, the redundancy. Oh, the redundancy. Yeah. Oh, isn't it odd that the instruments give you a decimal part, which comes from the instrumentation? So, which means that there is a phase shift, in this case, phase Doppler. There is a phase shift. There is a calibration curve, right? And that calibration curve will give you a certain phase between the four multipliers, and this will convert itself to a decimal part. Now, why? Why is it not random? Why it has all those regular points? For me, it's a limitation of the instrument. And one of the things I thought about was, well, we spend so much money with the phase Doppler, more than 100,000 euros. and we spend so much money in everything. But perhaps the most important part is to accurately measure the integer of the diameter. So, for example, if I have droplets which are on the range of 10 to 100 microns, I just, with this simple experiment, which is I did in the last few weeks, I thought if I accurately measure the integer part, then if I want to, let's say, have more detail in my measure for example, doing fittings of mathematical functions and so on, then I could add randomly the decimal part. Because
and you mean
apparently it doesn't mean anything. It's redundant.
Yes, and you mean maybe shadowgraphy is enough for our accuracy.
Exactly. So I honestly am very curious to, this is a hypothesis, let's say. I'm very curious to see how far we can go with this.
I'm so happy to hear this, because I think so about this, but I can't prove this topic to other people.
Yeah, but this, I think this is very, this simple experiment shows that redundancy is an important topic in information theory. Because in information theory, basically, is what is the minimum amount of information that you need to, let's say, your message is understood on the other side, right?
Mm-hmm.
And we strive so much in our techniques to have as much precision as possible, when eventually part of that precision actually is redundant. So,
thank you.
I don't know.
Thank you.
I believe we have a question from Sina.
Yes, exactly. But Dr. Shafai has some comments because he turns on his microphone.
Okay.
So, Mr. Miguel, thank you very much for your presentation. It was very useful and intrusive, and opened a new windows on the post-processing of spread data. I also thank Professor Kebriai for her efforts in arranging this webinar. As a feedback and result, is it possible to obtain an idea from data analysis and information theory for setting up some parameters of spread measurement systems? For example, sampling time in a PDA system, okay? In other words, instead of post-processing and changing bin widths, we can get data that are favorite for our physical interpretation, and also getting minimum measuring data.
Yeah, sure. I mean, from my experience, the information theory will help you to. It makes this distinction between data and information.
Mm-hmm.
And what we need to extract the knowledge is information, not just more data.
Okay.
We have more data as long as that means more information, okay? And what does more information means? Perhaps you can easily understand by the launching of the dice, right? Why do we always need to launch a dice? Because we never know the outcome, right? It's a uniform distribution. So every time we launch the dice, we get useful information, right? To see if the dice add all faces with the same number, why should I launch the dice, right? I already know what's the outcome because all faces have the same number. So it's meaningless to have more data, right? So when we use this information theory to understand this difference, then we can use it to, let's say, make sure that you have enough information.
Yes.
Or to study the phenomena long enough to see if there is a change in the information it will give. For example, if there is a process which is transient and changes in time, it should produce changes in your measurements, right?
Yes.
And it reminds me of an example. There was a researcher who was studying a flow, and he was making laser Doppler velocimetry measures. And the data rate was really, really high. Because it was really, really high, in, let's say, a few seconds, 1 to 2 seconds, he already had the 10,000 samples that the usual way of viewing the accuracy of a measurement would tell that he had. So he just took those samples. But he took those samples in a few seconds. And the process he was investigating had a time scale which was larger than the time scale that the instrument was giving to have enough samples to say that the statistical uncertainty is low. So he was missing a lot of physical information, right? Because some of the things that the flow was going to show in data happened later. But because he had 10,000 samples after a few seconds, he stopped measuring. But this phenomenon hasn't stopped happening, right? So this perspective from the information theory will look at these changes because it's sensible to these changes. So I think it will help us also to look at the physics, the underlying physics in spray events, which have a temporal component that produces eventually different outcomes in time, okay? So I think the information theory can be useful for that, but mostly I would say it's this distinction between data and having enough data or having enough information. I don't know if I replied to your question, but since we are working together, we can keep.
Okay, thank you again, and I hope I pursue this topic in our academic projects. Thank you.
Thank you so much.
I take the microphone to Mr. Atai to ask question. Mr. Atai, you can ask your question.
Hi, can you hear me?
Yes, perfect.
Yes, thanks for your great presentation. It was very useful. I have two questions, actually. My first question is about statistical analysis. Because you are working with large data samples and sorting and extracting knowledge from your information, can we use other methods like machine learning methods or neural networks in your field? And my second question is about nanofluids, because actually your topic is can be applied to nanofluid sprays and nanoparticles. I want to know about the interaction between, for example, the structure of spray and dynamic characterizations, and if there is any interaction between your field and structural engineering. Thanks in advance.
I apologize, Said, right? It's your first name.
Yes.
I couldn't understand in the first question the two methods that you referred.
Yes. For example, the statistical analysis that you mentioned, I think they are in classical methods, like the distribution you mentioned and the samples and the other fields that you mentioned. We have, for example, in statistical analysis, we have some other methods like machine learning or neural networks or some other algorithms.
Those names I couldn't understand it. Can you write them in the chat?
Yes.
Machine learning and neural network. Machine learning.
Machine learning. Oh, okay.
Yes. And neural network.
And neural networks. Oh, yeah. Oh, that's a very interesting field. if you are working with those methods in statistical analysis in sprays, yeah, move forward. That's very interesting. Because I remember at a certain point I wanted to use neural networks, and what I remember is that in those cases the physics is implicit. Okay, and for example, you may train a network to try and learn with your spray and how you characterize it, and eventually that could be interesting. And that is a field which is related with information theory. There are, I believe, some works which are using these techniques to eventually simulate events, spray events. Okay, let's say spray formation, spray impingement, and so on. And I believe that that's a very interesting research field that is not much explored. Okay. I'm not working in those fields, but I believe those are very, very interesting because the physics is implicit and they're basically unexplored. And as to the nanofluids, in the papers that I've shared, one of the last ones before the preprint, which is a paper from 2020 of Applied Sciences on spray characterization, when we test the explanations that we wrote about spray characterization, we actually investigate nanofluids, sprays made with nanofluids. And one of the things that we noticed is that the differences are not that large, which means that when you add nanoparticles to your liquid and you atomize it, there are some differences, I think mainly in terms of the velocity, which means that eventually the transport is a little bit affected. But in terms of atomization, in terms of producing droplets of a certain size, the differences are not that significant, which is useful and good from the, let's say, the application point of view, because in that case, the idea was to produce a spray that when it impacts on the surface is able to extract heat from the surface and improve that heat transfer, but we don't want to change the dynamics of the spray. I think that's a useful information because if people are thinking about changing the thermal properties of the fluid, they are a little bit, let's say, secure that they can use a certain characterization made without those nanoparticles and still get the same sizes and velocities, even if then you add nanoparticles, which we found useful information. But obviously, it depends on the concentration of nanoparticles that you use. However, you usually don't use a very high concentration to produce the change that you need in the thermal properties. And in order to avoid the agglomeration of the nanoparticles, you use a certain, how do you say it? Use a solution, a certain solvent. And that solvent, to avoid the agglomeration of the nanoparticles, is the one who produces the largest differences in the spray. But you can find more information on this in the paper, in one of the papers I have shared in the file. So, and in those papers, I believe you have also other references. And there is a colleague of mine, Professor Ana Moita, who is working on that. And you can, just follow the references and you will find more work on the nanofluids and sprays. I don't know if I answered your questions, but machine learning and neural networks, very interesting field. I think it has future in terms of the simulations because the physics is implicit and they're, I believe, much faster to process and to get results, but you have to train and so on. And in terms of nanofluids, nanoparticles shouldn't produce the biggest differences in spray production. The biggest differences will be in the solvents you use to avoid the agglomeration of those nanoparticles.
Oh, thank you so much. And Sina's question that if at the first he thanks for your presentation. And then he asks that how is it possible to relate the information or knowledge extraction from data in atomization process with other chaotic case studies?
Yeah, that's a very good question and observation. I recently read, it's behind me, a book by James Gleick, who's a writer on chaos. And while I was reading, honestly, I just kept popping in my mind the spray characterization and the way I was trying to use information theory in spray characterization. So I sense and I have this intuition that chaotic studies are helpful in developing this spray characterization research field. Also because the formation of a spray is a chaotic process. In some secondary breakups, for example, if you have a large droplet and there is a very high air field interacting with that droplet, this droplet will deform into, let's say, a pizza shape, and it will break into a chaotic event. So from my point of view, chaotic events, chaos theory, and so on, may have some tools, some interesting tools that could advance a little bit more, or eventually much more, the spray characterization research field. So if you are interested in searching for this link, I think it's a very interesting topic, honestly. And I'm also looking into that because I'm extremely curious. I don't know if I answer your question, Sina.
And the next questions, Mr. Ibrahimi, a big question he had.
Yes.
I'm so grateful to be in your webinar, and I have a question that you mentioned. The decimal can be ignored because its influence with compared integer is so small, but I think we have to put a limitation for it. For example, for the main diameter of 10 to 20 micrometers, decimal ignoration can be had from 5 to 10% error. Is it acceptable to give criteria for it? For example, for the mean diameter of more than 20 or 30 micrometers?
Yes, like I said, what I showed was a curiosity. So obviously, if we want to formulate the hypothesis, first we need a research question, a physical phenomenon, and so on. But if I understood correctly your question, for example, an integer with the value of 1, it's very different from an integer with the value of 20 or 50 or even 100, right? And for example, if there is a spray, like for example, an aerosol from this coughing and from this sneezing, where droplets fall into, let's say, an order of magnitude range between, let's say, hundreds or tens of nanometers to, let's say, the first order of micrometers, then the decimal part, it's different, because when the droplet is expressed in terms of nanometers, the decimal part is not the same when the droplet is expressed in terms of value in micrometers. For example, a droplet that you measure and has the size of 0.5 micrometers, in terms of nanometers, it means 500 nanometers. And so the decimal part will be very different, right? So from what I've understood so far, because this is very, very new, is that this idea of redundancy should be investigated when you have an appropriate range. So, for example, in this case that I've shown, if I have particles which fall into the range of the nanometer and of the micrometer, if I want to do any research on the effect of redundancy, I should do in the lowest order of magnitude. So I should do it in the nanometer. What does that mean? It means that 0.5 micrometers, I should investigate it as 500 nanometers, right? And a droplet that has 1 micrometer is 1,000 nanometers. I should make my research on the nanometer order, and any influence of the redundancy should be on the lower order of magnitude. That's my intuition, but as I said, I believe it's an open field. It's a curiosity, basically, that led me to think about instrumentation, basically. But I think it needs, obviously, more thought and more research. I don't know if I answered your question, but if you have any more doubts, just feel free to ask.
I appreciate you, Dr. Panel, because of the nice presentation. We would enjoy that. Very nice. If any other comments that we have, we can hear, or if we don't have, we can say goodbye to the others.
Okay, and I've uploaded a file that you can, download, which has several papers that were my work for these years on this topic, and I hope you find them useful for your research. And
yes,
that raises more questions than gives you answers. That's always the purpose of the papers I try to write.
The last file in the upload center that is named Statistical Characterization. You can download it and use it for your questions. Thank you so much.
Thank you so much for the invitation. Thank you for listening.
Again,
it was a real pleasure. And thank you, Azadeh, for the invitation as well.
Welcome, and thank you for a nice presentation and answer our questions.
Thank you. Thank you so much. And have a nice day, as much as possible.
Have a good time, and also have a nice day, too.
Thank you so much. Thank you so much,
Thank
all.
you. Thank you.
Okay.
I should say goodbye and have a nice day.
Thank you so much.
Goodbye.
Okay.
Thank you. Goodbye.
Bye-bye.